You all shy? All right. Well, the primary voltage will go on the x-axis. It's always y versus x. All right. Always a plot of y versus x. Therefore, we will have to put the y-axis, on the y-axis Vs, and that's the secondary voltage. And on the x-axis will be Vp, which is the primary voltage. And when they ask about the gradient or S or slope, it is based on the equation for a graph that indicates where you would put. Give me a minute. Right. Forgive me for that interruption there. So what I'm going to be doing at this point is I was trying to do it in Excel, but Excel wasn't really working for me. So what I'm going to do is I'm going to bring up an app. I'm going to deviate from the share screen a minute, and then I'm going to bring up an app that is able to do the drawing of the graph real quick. All right. So I'm going to sketch this graph really quick to give you an idea as to how it ought to look. All right. So remember, just bear in mind that this is a sketch, and at best, it is how it should look. All right. You would have in your exam grid and all of that. So you would not have to be doing what I am doing right now and trying to sketch. All right. But nonetheless, the same concept will apply in terms of drawing the graph. Just trying to get this thing to work with me here. Hopefully, okay, that's better. All right, good. Now, in terms of the data, I'm gonna have to toggle between, but as I said, the primary voltage goes on the X, so that's 1.5356. But in terms of the drawing of the graph, you have to ensure that your values are evenly spaced. All right, you have to ensure that your values are evenly spaced. All right, so that's like one. Let's see if I can get evenly spaced. One there, two there, three there, four, a five there, a six. No, that's not straight. Six, seven, eight, nine. That's one. That's a two. That's a three. And bear in mind that graph questions are unavoidable, and they're always question number one in the exam. So it'd be best if you familiarize yourself with graph plotting from now. If you have not done so, if you are, that's good. Remember that this time around it'll be two papers, so you will be getting graph work in this upcoming exam. So it is best for us to familiarize ourselves with that. Now, for the sake of the values to be put on the y-axis, I'm gonna have to use a smaller scale. Now, a scale is essentially 5, 10, 15, 20, 25, 30, 35, 40. I'm gonna have a little challenge there. What I'm gonna have to do is go up by 10 based off my values. You do not have to use the scaling that I'm using. It is because of the limitations that I'm working with here, why I'm using such a small scale. Now, a scale is essentially how your values correspond to your centimeters on your graph. So typically a graph comes with some centimeter spacings, and you have to now fit in actual values. The rule is that you use up as much of the graph paper as possible, and then you will write a scale at the top right hand corner of the graph to indicate what scale you have used. So with this scale I'm using, and these are secondary voltage, use V, S, And then please remember to label your graphs. All right, these things I know you probably would know already, but I'm just reiterating this for the purpose of ensuring that I cover all bases with you. So your labels with units, voltage secondary in volts, voltage primary in volts. Your scale goes to the top right hand corner. My scale on the y-axis is 10 units for every centimeter. And for my x-axis, it is 1 unit per every centimeter. You have to write these things. All right, it's good practice. All right, now in terms of the plotting of the graph, 14 on the y to 1.5 on the x. 14 is somewhere here. Let me use a different colored thing. So 14 is way about midway between 10 and 15, and then 1.5 is somewhere here. And of course, you'd have 0, 0. All right, so you'd highlight that. Then 14.5 to 14 to 1.5. 26 to 3. 26 is about halfway, 20 and 30. 3 is about here. And then we have 45 to 5. 45 to 5 is about here. And then 53 to 6. 53 is about here to 6, which is about there. And then we have 67 to 7.5. 67 to 7.5, which is about there. And then the final one is 72 to 8. You're probably not seeing these values. If you have the paper, it's a 2019 paper 2 for physics. All right, 2019 paper 2. All right, now with this comes our line drawn, which should look pretty much like that. You can change the color so you can see it clearly. All right, and then of course you're going to be required now to put in your, I'm not use that. I could change the color, couldn't I? Yes, I could. Alright. Let's try to ignore that. Let me use the other route. Let me use your imaginary, the other lines here. What I'm trying to get are the points of the gradient. Alright, so I'm trying to get out here. Alright, so just bear with me because you need to know how to calculate gradient. Alright, that's another point there roughly. And then that's good. And then another one would be here. Could use this one. You can use green lines to indicate that. That's good. And then that corresponding value would be, that doesn't really line up. Not use that one. All right. It's a bit time consuming, but I'm just going through the details. All right. So based on that, we have for our Y2 value, the Y2 value is the one with the green line. That's at the top. That's about 59, 60 thereabout. The Y1 value is the one with the red line, and this is on the Y-axis. All right, so the upper value on the Y is the Y2, the lower value on the Y is the Y1. So that's about, call it 60 and 35 for Y2. All right, we can jot those down just for clarity. All right, so Y2 is 60. Y2 is 60. Y1 is 35. All right. And then we have x1, which is the corresponding value for y1, which is 4, and then x2 would be 7. All right, you know the gradient is the difference of the y's, y2 minus y1. So the change of y would be the difference of those two, which is about 25. All right, and then the difference of the x's would be 3. All right, bear with me here, this mouse is acting up. So the change of x would be equal to 3. And then the gradient will be the difference of those two, which work out to be roughly 25 divided by 3, that's about 8.3. All right, so that's 8.3. When you divide the two, I'm just working in shorthand because of the limitations here. But yeah, that would roughly give you about 8.3 as your gradient. All right, so that is what you should get when you work that out. Now, going back to the question.
Sorry, I can go back so I can screenshot it.
Oh, all right, so sorry. Stop share. Let me go back to that. All right, there you go.
Okay, thanks.
Sorry about that. All right, good. So we have captured that and we see where now we can get the gradient from that. All right, now determine the gradient we just did. It was about 8.3 or thereabout. That will give you about 4 marks based on what we did. That would be the graph that you'd have to plot your thing. All right. Now, in terms of the rest of it, use the gradient to calculate the number of turns in the secondary coil, given that the number of turns in the primary coil is 85. Now, in terms of this, you need to know the transformer equation. The transformer equation relates voltage to number of turns. All right, does anyone know that transformer equation? Nobody? At all? All right, let's go back to the whiteboard. See if we can clarify that. All right. So what I'm gonna do here is I'm gonna have to open a new one. All right, I can put that as a shared thing for persons. All right, new project. Now the transformer equation is Vs over Vp. Well, typically it's Vp over Vs. Let me write it the way that they normally write it. So that's Vp over Vs. Alright, we know what Vp is, primary voltage. We know that Vs is secondary voltage. And the one that relates to now the number of turns is Np over Ns. Alright, that is the general equation. But your graph, and this is important, your graph plotted Vs versus Vp, which means that your gradient would have found what is Vs over Vp. So that means we have to invert this. For simplicity, invert all of this. Now, if we invert that, we would get Vs over Vp, which is equal to Ns over Np. Now, Np are number of turns. Ns is number of turns in the secondary coil, and Np is number of turns in the primary coil. So this is the equation that you want because the Vs over Vp is the gradient and Ns over Np is what relates to the gradient. Now, how does this tie into our question. Let me go back to that. Now it says the number of turns in the secondary coil is what you want, given that the number of turns in the primary coil is 85. So here we have the
You
gradient.
can't see the question, sir.
Not, how about now? It's good now?
Yes, sir.
All right. So Vs over Vp is what the gradient gives. Ns is what we want. Np is given as 85. So what we'd have to do now is transpose that equation that I just highlighted to find Ns. Now, if we transpose that the gradient is equal to Ns over Np, Ns would be Np times the gradient. All right. Are we all in agreement with that? Or is it because I just said so? Do you see why it is so? I need a confirmation. Anybody else can confirm? Nobody wants to talk? Why y'all so shy? All right, well, that's the equation that to use. So the 8.3 that we would have found for our gradient, 8.3 roughly, times the 85 NP would give us 705.5, and since you can't have half a turn, well, you could, but let's just round it off to 706. All right, so that's 706 as the NS value based on what you have gotten from the graph and what is given in the question. That's 4 marks. Now the next thing is to find what the current in the secondary coil is if the current in the primary coil is 1.8 amperes. Again, I'd have to divert to the screen for the whiteboard. Now, I'm going to make a slight modification to the equation that I wrote here. Well, it's not a modification, it's an addition really. And I'm going to insert now the part that relates to the current. Now, the addition is to put in now how the current ratio goes. So it is still current over current. But here's the trick. With the currents, where you have primary in the numerator for both turns and voltage, the current now becomes actually secondary. And where you have secondary in the denominator for both voltage and turns, the current becomes primary. All right. The reason for that is because of the equation for electrical power. V times I is actually a constant. And when you transpose our ratios, this is what you'd end up with. All right. Let me just put it at that. So just bear in mind, important, that current and voltage in terms of a transformer are inverse, so to speak, when it comes down to writing the ratio. All right. So we have primary in the numerator, current is in the second is in the numerator. We have primary. We have secondary in the denominator. You have primary in the denominator for current. So this is the general. If you want to take a screenshot of this, this is the general transformer equation. All right. This now relates current, voltage, and number of turns for a transformer. All right, this is the equation that you would need when working out transformer related questions. All right, that's a transformer equation. Now, how does this tie into our question? Let's go back to that. So we know that voltage and current are inverse. So Vs over Vp is equal to Ip over Is, or whichever way you want to write it. But we're given Ip, and we know what Vs over Vp is. All right, so our equation that you should use is Vs over Vp, which is from the gradient, without having to change that. And if you have Vs over Vp, then you would have equal to Ip over Is. So we need to find Is. So transposing for Is is what we need to do. All right, I have to be toggling back and forth from whiteboard to, physics is a lot of, is workout based. All right. So with that known, what you'd have to do, let me just rub out the bottom part here for the transformer equation. So what we're working with here now is Vs rather, for the sake of the gradient, is equal to Vp, which is equal to Ip over Is. And then when you transpose for, what is it that we're finding again? Is. You transpose for Is, you would have Ip goes now and cross multiplies to Vp. And then you'd have Vp. Or would us work it that way? No, you'd have to invert. Let me do it properly. So that would be Vp Ip, and that's multiply over Vs. If you do the transposition correctly, you will see this. The first thing you need to do is to cross multiply and get by the power equation. And then you would bring over whatever you know. So Vp goes with Ip, and then because Vs is with Is, when you transpose it, you would have Is in the denominator. All right. So it's Vp times Ip divided by Vs gives us the current that we need. And when that works out, we know what Vp, well, from a gradient standpoint, since you have Vp over Vs, let me just bring this out here. This now is Vp over Vs, but our gradient was Vs over Vp. So since it's our case, if you don't have the exact values, because you could just take values from the table, but if you don't want to do that, what you could do is just invert the gradient, because this would be the inverse of the gradient, and then multiply it by the current. All right, it says either you take values from the table, which is not always recommended, or you can just invert the gradient, because Vp over Vs is the inverse of the gradient, which is Vs over Vp. So that would be 1 divided by 8.3, which gives a decimal value, and we'll multiply it by that current. I think it was 1.8, yes. And then what we'd end up with is 0.2, roughly 2. If you do the calculation, you get that. So the current in this case for the secondary, current secondary is 0.22 amperes. All right. That is what you would get as your answer. Yes, because since it's a step up, the current will become less. So we're consistent with working. Just giving a chance now for anybody who wants to screenshot that. And then I can now move on to the remainder of the question. Now the power output of the transformer is what we need now, given that the voltage in the secondary coil is 55 volts. So we want the power output. So we're concerned now with everything at the secondary, because that's where the output is. So they have given us the secondary voltage. Here they now give you a specific secondary voltage, and we need now the corresponding current, because electrical power is voltage times current. That's an equation that you ought to be familiar with. So we have been given the voltage secondary. We need now the current for the secondary. Do we have it? Yes, because the question above asks us to find that secondary current. So this math is just to multiply whatever you got in the top question above that of the 0.22, which we worked out, by the 55 volts. So the 0.22 times 55 gives us 12.1, and since it is power, the unit of power is watts, and that's WTT spelling, and the symbol is capital W. All right, And that would be the end of question 1. Any queries, any misconceptions, any confusions at this time before I move on? No? All right. Can therefore move on now to the question 2. It says question 2. By inserting the appropriate physical quantities and the derived SI units. Physical quantities and units, physical quantity on the left column, derived units on the right column. Now, this is where I'd really want to get some feedback, because I know, you know I know, but I don't know if you know. Okay, so I want to find out from you, anybody, what your thoughts are on this table. So for physical quantity of volume, what would be the derived SI units? All right. There are about 5, or let me see how many persons are here. Nobody wants to talk. Participants. Brianna, not to call on anybody, but I'm calling. Is this Kellyanne? Is this Nikaira? Everybody else, Tasha Lee, Jarrett. There are about 4 of us here. Nobody wants to talk. It's not matter about you saying the wrong thing, you know. It's just about trying to find out where we. I'm saying the SI unit for volume. Right?
Cubic meter.
Say again?
Cubic meter.
Cubic meters. Very good. Thank you so much. Who was that? Brianna? Yes. Thank you so much, Brianna, for that input. All right. So yes, the derived SI unit for volume would be cubic meters or meters cubed. All right. We have now the derived units of kilogram meters per meter cubed, and that's kg m to the minus 3. In terms of the physical quantity attached to this, if it is possible, somebody other than Brianna could tell me what this physical quantity is. There's still. Say again?
Kilogram.
Kilogram?
Mm.
Not exactly kilogram, not exactly, because the unit is already kilogram, but we want the physical quantity. Just like volume is measured in meters cube, something has the units, when it is measured or stated, has the units of kilogram per meter cube. That's what I'm asking.
Density.
All right, yes, density is the correct answer. Thank you so much. All right, in terms of the end there, Newton, this should be an easy one. What is the
Force.
force? Lovely, thank you. All right, now, down at the bottom, we have 2 sections of units for pressure. There's the SI unit, and then there's the famous one that they normally quote it in. And they're equivalent, so you can use them interchangeably. All right, but there are 2 units that are commonly used for pressure in terms of SI units. Can anyone give me one of them?
I know one is PA.
And what does PA stand for? Do
Come
you
on, say
remember?
you remember.
PA, which is a capital P, small a, is Pascal. All right, PA is shortening for Pascal. So you are correct. I think it was Brianna or Kelly, I'm not sure.
Brianna.
Brianna, thank you, Brianna. All right, so that's one. Does anyone know the other one? No? All right.
It would be the same kilogram meter per second square.
All right. Yes, it is kilogram meter per second squared, but I'd want, how would it work out? Kilogram over meter seconds squared or something like that. But in terms of the SI unit, is the one that is what I want. All right. What do we use to calculate pressure? What's the equation that calculates pressure? You don't remember? Force over area, ring a bell? Right. That is the unit, that equation rather we use to calculate pressure. Now, in terms of the units, the unit would be newtons from force and meters squared from area divided. So the SI unit for pressure would be Newton per meter squared. All right, so that's the other unit that you can state for pressure being the SI unit. So the two units, pascals or Newton per meter squared, from the equation. Now, in terms of this question, a concrete block, figure 3, made with cement. It measures 140 centimeters wide by 2 meters long by 3 meters high. It says calculate the density given that the block's mass is 20,160 kilograms. All right, now density. What is the equation that is used to calculate density? It was mentioned up top.
Mass divided by volume.
Mass divided by volume. We have the mass. Mass is given. And we have and please, when you're looking at values given in questions, ensure that they are in SI units. All right? You have to know your SI units, especially for the first 5 or 7 fundamental quantities, mass of which is 1. So yes, mass is in kilograms, that's good. So we need to find the volume. How do we find volume of the shape? Anybody? So rectangular cuboid, how do we find volume of a rectangular cuboid? Length times width times height, remember that? Right. So these values of length, width, and height will be multiplied. But here's the trick. The units are not consistent. What do I mean? All the units of measurement should be the same for them to just be multiplied straight ahead. But that's not the case. There's 3 meters, 2 meters, fine, those agree. But there's 140 centimeters. Here's where CXC now wants to trick you. Don't allow them to trick you. Ensure that all units are the same and they are consistent across. So we have the two options. Either we convert centimeters to meter or we convert the meters to centimeter. The safer one is to convert everything to SI. So we convert the centimeters to meter. And to do that, what do we do? And I need somebody to talk to me about this because many of you know someone to know this. So what do we do when we convert centimeters to meter? Nobody remember? I want to know.
You're going to times it by 100
All
or
right.
divide.
Here's the thing. These are the times are divide. But the rule is small units to larger units, you divide. Write it down somewhere. If you're moving from a smaller unit, because centimeter is smaller than meter. So if you're moving from a smaller unit to a larger unit, you divide. And if you're moving from a larger unit to a smaller, you multiply. All right, so the 100 is correct, but it's not multiply, it is actually divide. All right, and just remember the rules. Small to large, divide, large to small, multiply. So we divide 140 by 100, which gives us 1.4. So we can now go ahead with our 1.4 meters with our 2 and our 3 meters to find the volume. So that's 1.4 times 2 times 3. That gives us 8.4 meters cubed. All right, so that's our volume. So to find density, we will just now divide our mass of 20,160 kilograms by our volume of 8.4. So that's 20,160, 20,160 divided by 8.4, and that gives a round figure of 2,400. Now the units of this density are the units of what you use to find it. Meaning, if you use kilograms and meter cube and you divide, then you will have to use the units there to report the density units. Do you want me to use the whiteboard to show this calculation, or you have your calculators and pen and paper and you're good? Let me know in terms of the calculation if you want me to show it. Brianna?
Yeah, that's good. I have to
Oh,
show it.
you don't have to show it. All right. So if there's a case that you want me to show it, don't be afraid to speak up and say, sir, show me what you say. Me is a visual learner. You can't bother there talk to me. I go fly out through one ears and go back through the other. Just talk. All right. So fine. So we have a situation where it is 2400 and the units are kilogram per meter cubed. All right, we'll go on to the next page. Now it says define the term pressure. Does anyone know a 2-mark definition for pressure? I mentioned it earlier on, so if somebody could just basically say it over in one sentence. Please tell me you were listening. You don't remember what I said about pressure? Pressure is the force per unit area, or pressure is that quantity where you divide force over the area which it acts. Any one of those. Once you bring out force over area or force divided by area, then you have given the definition for pressure. I would just with 2 marks right there. Now it says, given that the gravity constant G is 10 Newton per kilogram, calculate the pressure exerted on the floor by the base of the concrete block. Now, this is a trick question because you need to know what area this base really is. To do that, we look back at the shape. Now, as it is right now, we have to take it that this is resting on a flat surface. So we need now to determine which side, the area of the side that it is resting on. All right, because there are several areas. A shape like this has 1, 2, 3, 4, 5, 6 possible sides to rest on. But each of them have, well, they have different areas. All right, they have different areas. They're not all the same. So my question to you is, how do you now determine the area of the face that it is resting on? This is an interpretation question to see if you're thinking. All right, and it's just Brianna that's talking to me. I don't know if there are other persons here that are able to kind of interact with me. Is it possible? I see an Abby here. Nobody else wants to talk? Seriously? I'm not gonna be there by myself. Chat. Killian, Abby? Yes, Killian, I see your mic. I see your mic. Talk to me.
No, I'm just observing.
Alright. Like how I have captured. No, don't unmute. She gone. Yeah, alright. The area, the face, I know you see the shape, share screen. So my question to you, which 2 values would you use to find the area?
104 centimeter.
All right, 140 centimeters, and what
Yeah.
else?
And 2
2 meters. All right, but remember the 140 centimeters was converted to meter. What value was that? Remember,
Sorry,
all right, to go from centimeter to meter, we do what? Divide by what?
100.
Right, so 140 divided by 100 gives us what? Move the 1.4. All right, we just move the decimal place 2 places to the left. Divide, decimal place jumps to the left. 100 means 2 places. 1,000 means 3 places. All right, thank you so much for that input, Kellen. All right, so we're going to use 1.4. Clear this. 1.4 times 2, and that gives us 2.8. And since it is meter times meter, that is meter squared. So the area that the block is resting on is 2.8 meters squared. All right. And the next thing we need to know is the force, because pressure is force divided by area. Now, if we are given a gravity constant and we need to find force, which is weight. So the force an object exerts is its weight. All right, just by being in existence, it will naturally create a force called weight, and it will act downwards. So from the gravity given, and we need weight, which is a force, what else is needed to find that weight? I heard from Brianna and Kellen. Tasha Lee, you want to give a little input there? No, yes, no, yes, no. Kyra, I don't know if I pronounced it right. Nobody? Brianna, me go call upon you. You want to take that one?
What's the question, sir?
I'm saying if we have gravity, they say gravity is 10 Newton per kilogram, and we need to find weight of the object, which is the force we need. What else
Oh,
is
so it's
needed?
mass times gravity.
Thank you, Brianna. All right, so it is mass times gravity. And what is the mass? Brianna, if you don't mind me asking so many questions to you.
It's the 20,160 kilograms.
All right, thank you so much, Brianna. All right, so it is that 20,160 times 10 Newton per kilogram, which gives us 201,600 newtons. So that's the weight, which is a force, and the area is 2.8 meters squared. So to find the pressure, and as I said, if you need me to go to the whiteboard, say so now or while I'm working it out. So it is 201,160, right, divided by 2.8, and that gives a value of 71,842.9 if rounded off to keep the decimal place. It's like 857.85714. So I rounded it off to one decimal place. So that is 71,842.9. Now the units, of course, is the unit of the force divided by the unit of the area, which is the Newton per meter squared. So for those 4 marks, those 4 elusive marks, you would have to work out the area, 1.4 times 2, work out the force, which is the weight, 20,160 times 10 Newton per kilogram, and then you divide those two to give you the 71,842.9, and that would be Newton per meter squared. And that's our question number 2 completed. Number 3 we're on to. Define the term heat capacity. Does anyone remember this topic and the definition for such? No? All right. Heat capacity has to deal with the ability of an object to store heat and without its temperature changing. So really and truly, heat capacity is the amount of heat energy required to raise the temperature of a body or an object by 1 kilogram. That is how we determine heat capacity. So for the 2 marks for your definition, we need to say the energy required to raise the temperature of an object by 1 degree Celsius or 1 Kelvin. Remember, degrees Celsius and Kelvin are units used for temperature measurement, and the Kelvin is the more used one in physics because that's the more that's the absolute scale one. All right, so the definition, if you didn't get it, the energy required to cause an object's temperature to rise by 1 Kelvin or 1 degree Celsius. All right. Define the term specific latent heat of vaporization. There are 2 specific heats in physics. One that corresponds to freezing or melting, either way, and the other corresponds to boiling or condensation, either way. The one that corresponds to boiling or condensation is the vaporization. The other one is for fusion. So there's specific latent heat of fusion when something melts or freezes, and then there's specific latent heat of vaporization when something boils or condenses. Now the definition of specific latent heat of vaporization for 3 marks must include mass, mention of mass, mention of energy, and mention of what happens. So the definition would be as such. It is the heat required per kilogram of substance to change it from one state to another at constant temperature. So let me say that again. It is the heat required, 1 mark, per kilogram of substance, 2 marks, to change this phase or state of a substance at constant temp. Now you must mention at constant temp, because that is now what separates heat capacity from latent heat. Heat capacity is a temperature change process. Latent heat is a constant temperature process. And constant temperature means that the phase is changing and not the temperature. All right, so I hope those things are made clear to you. Part B, substance which has a freezing point of 80 kilograms was cooled, I said kilograms. A substance that had a freezing point of 80 degrees Celsius was cooled from 90 to a total solid at its freezing point. It says now, sketch a graph on figure 4 to represent the statement below. All right, this now I will have to go to my little whiteboard app to show you how this works out. All right, let me just open a new page. It's easier to just open something here. All right, now, in terms of, where is it? Looking for my shapes here. All right. I don't want the green line business here, but I could change it, right? Yes, good. Good, 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 good. All right, next line. So we're gonna be plotting, sketching a simple graph here. All right, let me go for my pencil thingy. All right, so them say 90 is up here. So them say yes. And then they say 80 is about here. Let me see if there's anything that I'm missing. No? All right, we have temperature on the Y and time on the X. But the important thing is that when you are plotting this graph, from 90 to 80 is a constant decrease. And then when you get to 80, it flatlines. And then over some time, it starts falling again. All right. So that is the important thing with this graph plotting. All right. You have to show that when it is a liquid and it is cooling, the temperature will fall from 90 to 80. 80 is the freezing point, and at that point, the temperature will remain constant over time, which indicates that it is now transitioning from the liquid state. And let me just put an addition here for clarity. So it is liquid at this point, and then when it hits the other end of that flat line, it will be now fully a solid here. And this will become very important for the remainder of the question. All right. So just bear that in mind. You can take a screenshot of this because I'm pretty sure you're going to need this info when you get to the remainder of the question, if I remember this question correctly. All right, so liquid at that point remains constant until it becomes a solid, and then it will continue falling after it becomes a solid, coming cooler and cooler. All right, good. Let us proceed back to the question. All right, so next page. A student conducted an experiment in which 1.5 kilograms of water at 30 degrees Celsius was converted to steam at 100. All right, assuming no heat loss to the surroundings, calculate the amount of energy needed to heat the water from 30 to 100. All right, now this is a combination question. What do I mean by combination? It involves heating from one temp to another, and it also involves a phase change because we started out with water and we ended up with steam. So there are two sections of heating taking place here, and it's a common thing for students to take it that this is just straight a temperature change situation. It's not. You do have temperature change and then a phase change, so that's important to note. Now, the first thing we need to find out is the amount of heat to heat the water from 30 to 100. That involves specific heat capacity. So once you deal with temperature change, then it's a specific capacity. When you're dealing with heat-related questions, always search and it's usually at the bottom of the question, always search for constants. And here we have our constants that we need. The first constant, specific capacity of water. We are given that, and note the units. Joule per kilogram per Kelvin. It can be in joule per gram per Kelvin, and the number will be different. Because if it's in joule per gram per Kelvin, it will not be 4,200, it will be 4.2. Because the difference between gram and kilogram is 1,000. So please note the units of your constants as well as your values. All right, and the specific latent heat of vaporization is also stated in joule per kilogram, and that is 2.3 times 10 to the 6, the actual value of which is 2,300,000. It's 10 to the 6 means times a million, and if you move the decimal places 6 places to the right, you will get 2,300,000. All right, so let that be clear to you all. Now, in terms of working out this question, we need the specific heat capacity of 4,200 joules per kilogram per Kelvin. We also need the mass, which they have given, of 1.5 kilograms. And the final thing we need is the temperature change. Not just the temperature given, but the temperature change. Now, the temperature change you can find in the last part of the question, which says heat the water from 30 degrees to 100. To find temperature change, we must subtract the final temperature of 100, whatever it is, but in this case it's 100, from the initial temperature of 30. All right, so all those three things will be needed because the heat energy is equal to the mass times the specific capacity times the temperature change. Those three things. All right. So we have the mass, we have the specific capacity, and we have the temperature change. So what we do now, as I said, if you want clarity, I can go to the whiteboard. If not, we just work it where we are. So that is 1.5 times 4,200 times 100 minus 30 is what you'd write down, but that would give 70, and that gives a total of 441,000 joules. All right, 441,000 joules. The per kilogram in the specific capacity cancels the kilogram of the mass, and the per Kelvin cancels the degrees Celsius in the temperature change. Temperature change, the units of degrees Celsius and Kelvin can interconvert. You can use Kelvin to cancel degrees Celsius once it is temperature change. If it is not temperature change, you cannot. All right, you cannot do that. But yeah, the units can cancel, so you're just left with joules for your units, and it is 441,000 is your answer. Now, the next question, calculate the heat, the amount of energy needed to convert the water at 100 to steam at 100. Now at this point, I'm going to go back to that heating curve that I drew earlier on to make that clarification. Now here we have a liquid to solid, but it doesn't matter whether it's liquid to solid, solid to liquid, gas to liquid, liquid to gas, it doesn't matter. When you are transitioning through from one phase to another, the temperature will remain constant. And what we need to know is that at one point, at one end of that flat line, there is going to be one state, and at the other end, there will be another state. So, and then I believe I'm going to just draw this because I know that some persons probably weren't exposed to this. So I want it to be clear, 100% clear, so there's no confusion as to what I'm talking about. So I'm going to take time to explain it. But it is very important. And it can mean you missing out on a lot of marks if you don't get it right. So bear with me here, please. Now, for a typical, how do I put it now? Let me just, oh, really? Need a pen, right, that's it. Now, for a typical heating curve for water, it will have this basic shape. All right, and we have one point here, we have another point here, we have another point here, we have another point here. All right. Down here will be ice. Here would be water. We're talking about the phases here. Right, water here. We'd have steam here. All right. And then we'd have these points that I just highlighted. All right. This would be ice plus water. All right. Ice plus water would be here. And then up top, we would have water plus steam. All right. So what we have here are the different sections of a typical heating curve. And for the cooling curve, is just the reverse. Instead of going up, you'd be going down. All right, but this is what you'd have in terms of the water, steam, ice, water, right? Now, for the question at hand, we're starting at a point of 30 degrees. So that's 30 degrees will be somewhere here. And then we'd go to 100, which is somewhere here. So this would be like 30 here. And 100 will be up here. All right. And that will correspond to 100, that will correspond to 30. So what I need for you to realize is that for this heating process, and then we'd have over this point now where it is all steam. This point would be steam. All right, and that point would be water. That point at 100 would be water, and that point at 100 would be steam. So there are two sections, one where it heats from 30 to 100, and then the other one where it converts from water to steam. All right, so this is the second part that we're trying to find. You can just screenshot this if you want at this point. All right, so really and truly, there are two workouts. That is why they have two questions asking about energy. Now, for the second part, stop share. For the second part of the question, we're going to now be using the latent heat of vaporization constant, which is 2.3 times 10 to the 6. A latent heat of vaporization equation is energy is equal to mass times that constant. So the mass is the same, 1.5 water times 2,300,000, which gives us 3,450,000 joules. All right. So let's multiply mass by the constant, and that gives you the energy. All right. Now, the last part of the question, which is the easiest part, is to find the heat from 30 degrees to steam at 100. So we are now moving across the graph from one end to the other. So we simply know to find the energy, we would add this heat energy of 441,000 plus this heat energy of 3,450,000. So when I add those two, 441,000, I get a total of 3,891,000 as the total heat energy. All right. So that is what you would do to solve this question. So as I said before, heat from 30 to 100 is equal to mass times specific capacity times temperature change. That gives us 441,000 joules. Convert water at 100 to steam at 100 is equal to mass times latent heat of vaporization. That's 1.5 times 2.6 times 10 to the 6, or 2,300,000. That gives 3 million, and I believe it was 650,000, somewhere there. And then we add the two values and we get 3,891,000 as our final value, which is the answer for the heat, the water from 30 degrees Celsius to steam at 100. And that is the end of question 3, I believe. All right. We're on now to question 4. State 3 figures or features rather of an image produced in a plane mirror. All right. I will take it that, well, let me not assume. Does anyone know even one of these features of an image in a plane mirror? Nobody?
So I know of virtual.
All right, it is virtual. Very good. Thank you. It is virtual. Brianna, thank you. Anybody else wants to add a feature? No?
Sorry, I have behind the mirror.
All right, it is behind the mirror. Yes. But by virtue of it being behind the mirror, it makes it virtual. All right. But that is just another way of saying it is virtual, because a real image means, boy, you could have go feet and take it up. Right? It could be projected somewhere, but the mere fact that it is behind a mirror, and we know, so boy, behind a mirror there is nothing more than just images, right? So yes, so essentially it's the same thing.
So
Another
the image
one,
and the object are the same distance.
thank you, Brianna, again. So the image and the object distances are the same. All right, so if you stand 1 meter away from a mirror, just know that if you are able to measure where your image is, that image would also be 1 meter away from the mirror surface. So object image and image, object distance and image distances are the same, and the image is virtual. All right, and anything else that you remember?
Upright.
It
I'm
is
not sure.
upright. It is upright. All right. And it is, and another one that you could add is that the image and the object are the same size. So you don't look in a mirror and you see a bigger image or a smaller image of yourself. That's where lenses come in. They magnify or they diminish. But for a mirror, what you see is what you get. All right. Unless it's a curved mirror, which is something different. But a plane mirror, yeah, image and object size are the same, image and object distances are the same, it's upright, it's virtual, all of that. So any one of those 4 features you could have picked and put in feature 1, 2, or 3. Thank you for that interaction, Brianna. Explain why the word shown there, which is police, written as if somebody don't know how to write, is painted in this manner at the front of some emergency vehicles. Does anyone know? I know you probably would have seen it. Probably not police, but definitely ambulance. Right? Have you ever seen this? Question. Anybody? Or when you're looking at it? Okay. When you look at it, when they put it on the vehicle, they put it in this fashion where the letters are turned around and they are spelled in reverse. Right? But does anyone know why? Especially for emergency vehicles.
Not really.
Not really. All right. Have you ever, well, persons clearly would have looked in a mirror. Or even sometimes when you use your phone's front-facing camera, it happens to you. Left becomes right, right becomes left. They call it lateral inversion, fancy word, which basically flips everything. All right. So whatever you know to be on the right, when you look in a mirror, it ends up as being left. All right. So right now I'm holding up my right hand, and even though Zoom works out to kind of flip it in the correct way, when I'm looking, I know it's my right hand, but on the screen, it will appear left. All right. And when I raise my left hand in the mirror, it will appear on the right. All right. And even when you look at the hand itself, you know, the left and right hand are images of each other. All right. So what happened is that you have to put it this way because you're not going to, when you're driving, as a driver, you're not looking behind you. You should not be looking behind you. So for you to see the vehicle and know what it is, you'd have to look in mirrors, either the ones at the sides or the one up top inside the vehicle. So because you're using your mirrors to see behind you, whatever is projected in your mirror, if it is written correctly, it will come to you inverted. Do you agree with what I'm saying? Yes, talk to me. Right. So for you to see it correctly, when you look in your mirror, they have to know write it in the way that you would normally see it in a mirror. All right. So if you're looking at it in a mirror in a normal written way, you would see it in this fashion, as it is written now. So when you look in the mirror, it flips it in the correct sense. So you're seeing the word police as you should see it. And that's what it is spelled here. Police. Police. All right. So that is why. So to answer this, images in a mirror are inverted. So when you look in a mirror, for you to see the word correctly, you will now have to invert it when you're writing it. All right. So three things must be mentioned. Images in a mirror are inverted. That's the first thing. So when you look in a mirror, to see it correctly, you have to see it correctly in the mirror, you must now write it inverted in the normal way. All right, so you have to state that. Images are inverted in a mirror, so for you to see it correctly in a mirror, they must write it inverted. So by the time it gets to the mirror and to you, it's the right way that it should be. Make sense? Talk to me if I'm making sense.
Yes, sir.
All right, excellent. We go on to the next page. Figure 5 shows an incomplete ray diagram. And we have, what kind of lens is shown here? This lens that is shown here. I need for you to tell me if you know the lenses. What kind of lens is shown here?
Concave.
Good, concave. All right. So we have a concave lens and we have a ray heading parallel to the principal axis. The principal axis is this horizontal line where the F and F are on. All right. The optical plane is this vertical line. You know, you have to know the labelings of a lens. All right. So the principal axis, and then this here is the optical plane. Now the ray is this arrow with the arrowhead on it. Incomplete, they say. Complete the ray diagram to show the path of the emerging ray as it passes through the lens. Now the rule is, I could go to the whiteboard to show you what's up with this. But the rule is that any ray that passes parallel to the principal axis, when it hits the lens, it will be bent in such a fashion so that, all right, for this is a diverging lens. So for a diverging lens, it will actually operate in the other fashion as a converging. But let me just draw what would happen. Remember, diverging means that they spread out. So the ray now will spread outwards from where it would normally be traveling. All right, so let me just draw that principal axis. All right. Now I'm just going to be using the optical plane. All right, I'm going to be using an optical plane to indicate what happens. Let me use, this would be F on one side and the same distance roughly on the other side would be F. All right, this is the ray that hits the optical plane. Optical plane is this vertical line. Now what happens is that the ray would follow a path. Now this, let me just make sure, so you see it is a broken line. This is a broken line. This is a solid line. So the ray would actually follow a path when it spreads out, such that if you trace it backwards, it will be hitting the point called F. All right, so if it is parallel to the principal axis, the horizontal line, when it hits the diverging lens, which is the concave lens, it will go upwards, it will be bent upwards, and then that line of travel, when you trace it back, it must coincide with the F that is here. All right, is that clear to everyone? I need affirmation here.
Yes, sir.
Good. All right, so that is what would happen for that. On the diagram, label the focal length as being F. The focal length is simply where the F, capital F's are on the diagram. Let me just bring it up so you see what's going on. There's no host. All right, I've lost host privileges, Mike Town. Could you put me back on, please? All right, as we wait for that to come back up, as I was saying to you, where you saw the capital F's on the diagram, thank you. Where you saw the capital F's on the diagram, that is where the focal length would be. That is what is marked by focal length. All right, and it is also the point where that ray can be traced backwards. All right, so that's where you'd put your F, just so we're clear. Now, an object was placed 15 centimeters in front of a converging lens. So this is a different lens now. That's a diverging. We're now talking about a converging lens. A focal length 5 centimeters. It says calculate the image distance. Do we know the equation that relates focal length, image distance, and object distance? Do we know that equation? Yes or no? Yes, no?
Yes, sir.
All right, that's a no. All right. All right, let me just clear this. I'll take it that if you need the screen share, you would have taken it. So I'm gonna just remove that. All right, there's an equation that relates all three terms. U, V, and F are the terminologies that they use. The equation is as follows. 1 over F is equal to 1 over U plus 1 over V. Have you ever seen this equation at all, anywhere?
Yes, sir.
Okay. So we know what F is. F is a focal length, but do we know what U and V is? Do we know? U is the object distance. Thank you, Aston. U is the object distance, and that's in whatever units they have given you. Alright, so that's object, and V is the image. Alright, image distance. Alright, so based on the question here, we know that we want image distance, so we have to transpose for 1 over V. Alright, so transposing for 1 over V gives us 1 over V is equal to 1 over F minus 1 over U. All right, and that's also, of course, equal to the focal length in the question is 5 centimeters. We can just use 1 over 5 for the purpose of workout. And the image object is 15. All right. Now, when we find the LCM of this, that would be 15. That's a bit too close, a line. So that's 15 as the LCM. And that would give us 3 there, minus 1. Is that it? Yes. And that gives us 2 over 15 as the 1 over u, 1 over v rather. But to find v, we need to invert. So v is actually 15 over 2, right? And that gives us, gosh, this mouse is not working well at all. And that gives us 7.5. And that would be in centimeters, because everything was in centimeters. All right, so you can take a screenshot of that to know how to work that out. Yes, that looks correct. All right, screenshots taken. Going back to the question. Where are we? Right. So we have found the image distance for 3 marks. All right, the magnification of the imaged form. Do you know the magnification equation?
No.
All right, the magnification equation for bio students. You're supposed to know this, bio students. You know. Magnification equation is simply comparing image to object. And it is quite literally image over object size or image over object distance. You can use that as well. All right. It is size really from a biological perspective. That's what they use. But from this perspective, we can use image and object distance. All right, because the distances will determine the sizes. All right, so to find out, we know that from the previous question, you can bring it back, that the image distance, the object distance is 15. And we also know that from calculation, the image distance is, and I cannot share about that screen, is 7.5. So magnification, they usually use it as being M. Hope I can write it in this space made here. Let me use this ink. So M is equal to V over U, which is 7.5 over 15. And that would be reduced to 1 over 2, which is a half. All right, so that's 0.5. Whichever way you want to write it, whether a half or 0.5, it's really up to you. But, you know, we as physicists, we like seeing decimals to show that, yeah, you know math. Not to say that you don't know math if you write a half, but, you know, it shows a higher math ability when you write it in decimals. All right, so that's the magnification. And it makes sense. If you have something that's 15 centimeters, and then it passes through a lens and it goes down to 7.5, then it has been reduced by a half, or the magnification is a half. So it has been diminished. All right, when you have magnification less than 1, it is diminished. If you have a magnification greater than 1, then it's magnified or has been enlarged. All right, so yeah, you can have those coming out. All right, back over to the question. So I think that's the end of question 4. Yes, it is. So we're on to question 5. Circuits. All right, typically this part of physics now, some persons have a challenge with, a major challenge. So I may have to go a little bit slow here. All right, a semiconductor diode. Before even going no further, do we know what a semiconductor diode is? Need a yes or no? Hello? Talking
Yes.
to. All right, Brianna, I don't know what you just said. Is it a yes or no, sir? Yes or to what? Do you know that them? Brianna, talk to me now, man. Don't get too shy again.
No, sir. It's because my auntie have class, so it's kind of noisy in the
Okay. Okay,
background.
understood. All right. In terms of the half-wave rectification, as component called semiconductor diode is used, which is basically a one-way valve. for current. All right, it allows current one way, but it doesn't allow it in the opposite way. All right, just think about like a valve in a water pipe. It allows flow one way, but if the water tries to go back, it doesn't allow it. You know, sometimes, especially in the Manchester area, we have to put on those things because when the water goes, especially if you have a drum and you store water, it can run back out into the main. So it is recommended that you put a one-way flow valve on those pipes or anywhere at all, because I've seen it even happen where pressure is high, right? When you're putting on those things, you have to put on a one-way flow valve so the water flows from the road to your property and not the back way. Because if you allow it to flow the other way, then whatever water you have stored will run back out into the line, and then you will be rather upset. So yeah, the semiconductor diode works that way, where it allows current only one way in a circuit and not the other. In terms of this term, half-wave rectification is a fancy term that really is talking about alternating current. You know, alternating current goes up and down like a transverse wave. The diode cuts off half of that. So if it is the upward pulse that it allows, it doesn't allow the downward pulse. The upward half cycle, yeah, downward half cycle get cut off. So you just have up a gap, and then that is the making of rectifying. Rectification is just simply converting alternating current to direct current. And you need diodes to do that, but diodes prevent the two-way flow. All right, and then you have some like a fancy working out where you take that half that was cut off and you flip it so it goes the same way. But we're not going to get into that. Just know that the diode is a one-way flow valve for current. All right, now sketch an IV graph for a semiconductor diode. IV graph for the semiconductor diode. All right, what I'm going to do, I'm going to screen share this. It'd be easier to show it on a screen share. IV graph. Easier for diode. It'll be easier to share this. So you see what's up. All right, let me just stop sharing this. And then share. That's it. All right, let me just bring this. Which one is a more simple? All right, we use this graph. All right, so we're looking at this graph here. All right, current voltage. So what they're showing here is that the graph is not as you'd expect it for an Ohm's law graph where you have a straight line through current and voltage. Instead, you have it being almost zero up to a point. As you increase voltage, no current flows up to a point, and then the minute it exceeds that voltage that it wants to flow, then all of a sudden the current starts dumping. All right, and this is in the forward flow or forward bias arrangement. All right, there's forward bias and there's reverse bias. Forward bias means they connect the way you'd want it to connect and the current flow the way you want it to flow. Reverse bias means it's just simply the opposite way. For the reverse bias, it will prevent the current from flowing up to a certain voltage because it's a semiconductor, so you can't really handle much voltage. So the minute you exceed that breakdown voltage, they call it, then it starts to dump current as well. So up to a point, it can conduct, it can prevent current. But if you exceed the built-in voltage, then it just going to give way. Right? But the important thing is that this is the shape that they're asking you about. So if they ask you anytime about the IV for a semiconducting diode, this is pretty much what you draw. Current on the Y, voltage on the X, and you draw this funny looking curve thing. All right, but yeah, that is what they're asking about when they ask you about the IV characteristics of a diode. All right, so that's for 2 marks. And that's the 2 sections. You have to draw the 2 sections. You can see current on the Y, voltage on the X. So you draw something that goes flat and then it goes up, and then the back part of it now goes that way all the way out, and then it just drops down sharply. All right. Logic gates, another part of electricity that persons have a problem with. Complete the truth table in table 3 for a NAND gate. Now, does anyone know what this whole NAND gate thing is?
Yes, sir.
All right, good. Do you know what the truth table of a NAND gate is, Brianna?
Yes, sir.
All right, good. So talk to me then. What is a NAND gate output? What would it be under the output column? There are 4 sections. Oh,
You
and
have triple one and 0.
triple one, then 0. All right, lovely. Thank you. For persons who don't know, A and B are the inputs. NAND gates are electronic switches or electronic regulators for digital input. Digital, binary, 0 and 1, right? So what it does is that it takes inputs, 0 and 1, at 2 input points, and then based on the logic it has, it will give a certain output, which is either a 0 or a 1. For the different gates, you have different truth tables, which will look at the 4 possible inputs, 4 possible states of the inputs. And for 2 inputs, if it is 3, it's going to be more, but for 2, it is 4 possible: 0, 0, 0, 1, 1, 0, and 1, 1. Right, there's nothing else that you could add to 2 inputs in terms of binary. And then the output now, based on the type of gate, would either be a 0 or a 1, as I mentioned before. Now, as Brianna rightly said, it is triple one, and then a 0, which means 0, 0 is a 1, 0, 1 is a 1, 1, 0 is a 1, and 1, 1 is a 0. All right, these things you'd have to know. The truth tables you'd have to know. Find a way to know them, and please go into exam knowing them. There's no other way I could put this. All right, I don't want to run up. See how much marks you carry? 4 marks. And I just put on either a 1 or a 0 in the correct place. So please know your truth table. There are 5 of them: a NOT gate, OR gate, AND gate, NAND gate, which is this, and the NOR gate. All right. The NOT and the AND go together to give you the NAND. The NOT and the OR go together to give you the NOR. If you really look at it, the and the NAND are just inverse of each other. For the
So
AND,
we
you'd
have a
have,
4 gate.
say again,
Don't we have a 4 gate?
a 4
Yeah,
XOR
I think
gate.
we have a 4 gate FOR. I think we do.
Hold on, one minute ago. And this is one of them new edge gate then. I know you have an XOR gate and an XNOR gate. All right, when you go like cape level, I know that there's XOR and XNOR, exclusive OR, exclusive and exclusive NOR, right? I know that those gates exist, but for a 4 gate, I'd have to check that out. Not saying it doesn't exist, because I don't know everything, but in terms of
Yeah,
the 4,
sir.
all right, but I'll check it out still. But for now, for CSEC, I know definitely for CSEC, not and or NAND and NOR. Those 5 gates are what you should know. All right. And as I said, the NOT gate is an inverter. It's either 0, 1, 0 input, 1 output, 1 input, 0 output. So it just flips it. And then you put the flipping or inverting characteristics with the other gates to give you the NAND and the NOR. All right. So that is a little info there if you weren't aware. All right. Moving on. Circuits. Again, we're dealing with resistors. Now, 3 resistors in series. Very important to know how they're connected. Is either series or in parallel. This is now in series. The values: 2 ohms, that's the symbol there, 5 ohms, 10 ohms. Calculate the equivalent resistance of the resistors shown. Does anyone know how do we find the total or equivalent resistors of resistors in series? Anybody?
Yes, sir. I think I kind of remember.
All right, tell me what you kind of remember.
For resistance, I think it's R1 plus R2 plus R3.
Thank you, that is correct. All right, so when resistors are in series, we just add them as we normally add any number when we're adding, which is the R1 we can take as 2 ohms, R2 5 ohms, R3 10 ohms. So it's R1 plus R2 plus R3, 2 plus 5 plus 10, that gives us 17, yes, ohms of total equivalent resistance. If they were in parallel, it would be a different story. But thankfully, it is not in parallel because parallel is a little bit more complicated, just a slight bit more. For some, well, see there? We have go there now. All right, so they are now in parallel, and they ask you the same question. What is the equivalent resistance here? Anybody, whether it be Brian or otherwise, do you remember or know what the equation for resistors in parallel are in terms of equivalent total resistance? All right, everybody get quiet. All right, Brianna, you were saying?
It's R1 over R1 plus 1
Mm-hmm.
over R2 plus 1 over R3.
All right, thank you so much. 1 over R1 plus 1 over R2 plus 1 over R3. For those who don't know what she's talking about, let me just go here and make that clear as to what exactly is this whole equation thing she's making mention of. All right, let me just bring up. All right, so it is 1 over RT, and RT is the R total, is equal to 1 over R1. In the general, this is just a general equation. We know that the R values can change to whatever they want to be. But this is the general equation. 1 over R2 plus 1 over R3. All right. So that gives us, what was it, 2, 5, and 10? Yes. 1 over 2 plus 1 over 5 plus 1 over 10. All right. And we know we do the LCM. And the LCM here would be 10, because 2 can go into that, 5 into that, 10 into that. So 2 into 10 is 5. 5 into 10 is 2. 10 into 10 is just 1. So that's 5 and 2, 7 and 1, 8 over 10. Now, please bear in mind that this that you have found is 1 over RT. To find the total resistance, and this is very important, we invert 1 over RT as well as invert what 1 over RT is, which is 8 over 10 giving us 10 over 8. That reduces 5 over 4, which is 1 and a quarter, or 1 and a half. 1 and a half. No, not 1 and a half. 2 and a half, actually. No, yeah, 8 into 10, 1. 2 remainder. 2 over 8 is 1 over 4. So it's 1.25, actually. Using the whole brain here to work out it. All right, so that's 1 over 1.25 ohms as the value of the total resistance. And it is interesting to note that you have 2 ohms, 5 ohms, 10 ohms. When they're connected in series, they give a total of 17 ohms. Here, in parallel, they don't even give 2. They give 1.25 ohms. So what you should be aware of is that when resistors are connected in parallel, the effective resistance decreases. When they're connected in series, the effective resistance increases. When they're connected in parallel, the effective resistance decreases, as you can see from the math shown here. All right, so that's how we find the effective resistance of the 3 resistors that are in parallel. If you want to screenshot You can do so now as I transition over to the remainder of the question, and I'm doing so now. Right, so we have found that the resistors in figure 8, which is that with the parallel, were connected to a circuit with a 6-volt power supply. Calculate the total current flowing through the circuit. This now requires Ohm's law. Can anyone recall what Ohm's law equation is? Nobody? Nobody at all? All right. Ohm's law equation states, Brianna, yes, you were saying?
Oh, yes, sir. Not the Ohm's
Yeah, what about Ohm's law?
law. IR.
Thank you, V equal IR. But here's the thing now, we're not solving for V. We want what? Current. So if we transpose to current, what do we end up with? It's a simple transposition, people. Come on, man. If V is equal to IR, then I is equal to
V over R.
V over R. What is V? The 6 volts that they told us. What is R? Since they were working with the resistors in parallel, R is that 1.25. So we would have to divide 6 volts by 1.25 rather, ohms. And that would give us, that'd be the same as 10 over 8. Let's draw for the calculator so I don't make any mistake. 4.8, and that would be amperes. 4.8 amperes. All right. So that's our current total for that circuit. If you want to screenshot, you can do so now as I transition to the rest of the question now. And that's it for question 5. Alrighty. So we can now move on to question 6. Radioactivity. Lithium-7 is an isotope of lithium. That's how it's read. The mass number is 7 and the atomic number is 3. Use information above to determine the number of protons and neutrons present in an atom of lithium. Protons, neutrons. Now this is where I'm going to ask persons to tell me what these numbers are. First, the proton.
It would be 3.
3 for protons, correct? Because the atomic number and the proton number are the same. And what is the number of neutrons?
4.
4. How did you get the 4, Brianna?
Subtract the atomic number by the mass number.
So we subtract the atomic number from our mass number. All right, thank you so much for that feedback. Clearly labeled diagram of the structure of lithium atom rather. Now you may say that how them ask me chemistry in a physics exam. They're not done wicked already. If you put me in a physics exam now, they ask me chemistry for later. But yeah, this aspect of physics overlaps with chemistry. So if you are not so familiar with your bonding diagrams in chemistry for the chemistry students, please get so. And even more so for those who don't know chemistry, it is important that you do know these things. Okay, so let us transition to our whiteboard, or what I have deemed it to be our whiteboard. Come bother to be, probably would be easier. Let me just do that save. Thank you very much. All right, we're back to our place. All right. Now, first thing we need to do is to demark our nucleus, and then we show where, probably I should have done that first. So we write out our neutron 4n and 3p. That indicates our proton and neutron count. We mark it around to show that's our nucleus. And then we mark our shells around that and use a different color so we can differentiate shell from nucleus border. All right. And then we start putting on electrons. Start putting on electrons. I use a different color for electrons. All right, that's one electron I'm using cross. You can use dots if you want. But for clarity, I'm using the cross. All right. Keep it good. And then we add another electron. Now, the reason why I added 3 electrons is because for an atom, the electron count must be equal to the proton count. So if there are 3 protons, there must be 3 electrons for the atom. And I stress it being the atom. If it is an ion, it's a different ball game. Ions have different number of electrons from protons. But for an atom, they're all the same. So the nucleus with the proton and neutrons, the first shell with the first 2 electrons, the second shell with the third electron. And just to show off that you know, you can just add the symbol, the mass number, and the proton number. And if you really
I
want to
thought
get,
of the configuration.
and if you want to get geeky, you can add electron config. All right, and that's a 2 and a 1. 2.1. I don't know how your teacher teaches you to write it, but that's how I write it. All right, electron config to show how that is. All right, so I don't think there's anything else that can be added to this, no? So that's it. As for your lithium atom, showing everything in terms of arrangement. All right, moving on, back to the question. Clearly labeled diagram, that's our clearly labeled diagram. In 4 days, the activity of a sample of lithium decreases to 1/16th of its original activity. Define the term half-life. Does anyone know a definition for half-life?
So, half-life is the time required for a quantity to reduce to half of its initial value.
All right. I like that. I like that. That sentence sounds to me like full mark. So it is the time it takes or the time required for a sample or a substance that is decaying. Normally we add radioactive substance or radioactive nuclei. But it's not just any substance. It has to be something that's radioactive because radioactive substances will decay and they will decrease in the amount over a certain time period. And the time period for half of that radioactive substance to decay, or half of the radioactive nuclide to decay, is termed as the half-life. All right, but yes, what you have told me is sufficient. All right, and the last part of that question, calculate the half-life of lithium. Now, the straightforward way of doing this is to look at how many half-lives have expired by reducing it to that value. All right, there's an equation. I'm trying to recall the correct equation. I think it is 1 over the 2 raised to the, trying to recall it. I'll slip my mind right now. Now I'm just trying to recall the equation that let you solve directly for half-life when you know the amount that it has reduced by. I'm trying to recall that equation. But in any case, the reason behind it is that, let me just look back at it. 1/16th, and in 4 days it reduces to that. Okay, so after 4 days it reduces to that. So the other way you could look at it is to say, all right, to get to 1/16th, you want to look at now how many half cycles it has gone through. First half-life, it would have dropped to half. Second half-life would have dropped to 1/4. So it's a half of a half, which is a quarter. Third half-life would have dropped to 1/8, which is a half of a quarter. And the fourth half-life would have dropped to 1/16, which is a half of 1/8. All right, but they ask us to calculate. So I'm just trying to recall that equation that relates the amount, the half-life of the substance. All right, hold on, let me just T half-life. I know that 2 to the n is equal to, yes, n naught over nt. I'm just trying to get, so the initial amount is 1 over 1/16. Gonna have to bring up that equation now. I'm gonna put a pause on that because I want to give it a direct equation, but it's evading me right now. So let's move on to the other question. I'm gonna double back to this one. All right. This one now. Calculate the energy given off in a nuclear reaction and the change in mass is 0.2014 U. Now, this equation, this question is related to Einstein's famous equation of E is equal to mc squared. E is the energy, which is what we want. M is the mass of the substance in kilograms, or the mass deficit. The mass deficit or mass defect. Those are the two terms that I use. Mass deficit or mass defect is what the mass is talking about. And the c squared is the speed of light squared. Now, they have not given you mass in the usual units because they said that if the change in mass is 0.2014 U, but you need mass in kilograms. The speed of light constant is given 3 times 10 to the 8, but we need the mass. So what needs to happen is that we need to convert the given mass in this U value to the mass that we need in kilograms. To do that, we simply multiply the U value given by the U constant. Now, U is the atomic mass unit. Yes, Emily. Yes, Emily. So the U value here is simply the mass deficit that is given, and then the actual mass is converting that mass deficit in U to actual mass by multiplying the two. The atomic mass unit is just a convenient representation of atomic masses for very extremely small particles, because really and truly, there's no way for us to directly measure 1.66 times 10 to the negative 27 kilograms. We don't have an instrument to do that. So scientists, as usual, come up with convenient ways to quantify matter, and it doesn't matter how small the matter, they have found a way to quantify it, and they use the atomic mass unit. So that's where that came from. So the calculation is simple. We multiply the U value by the actual mass, and then whatever we get in kilograms, we multiply that by the speed of light squared. So to measure the U value, it is 0.2014 times 1.66 exponent negative 27, and then we get a value of 3.34 times 10 to the negative 28. Once we have found that, give me a minute. Right. So once we have found the mass value, it is 3.34 times 10 to the negative 28 kilograms. So that's our mass in actuality. Now to find the real value of energy, we'd have to multiply that by the speed of light squared, just 3 exponent 8, and we will square that. And the overall value of energy is 3 times 10 to the negative 11 joules. All right, so remember, we multiply the U value by the kilogram of 1.66 times 10 to the negative 27. And then whatever value we get in mass, which was that, I don't remember what it was, but it was 10 to the negative 28. And then we multiply that by the square of speed, and then we get a value of 3.0 times 10 to the negative 11 joules. All right. Now, in terms of the question that we were looking at earlier on, we have to go back to that one. Right, so let's go back to the question of the half-life of lithium. Now, in terms of the workout, I have to stop sharing that and go to the whiteboard that we had. All right, we're just in time now to finish up, so let's look back at that. Now, as I said, you can use the approach that I just told you to show you that after one half-life, it is one half, two half-lives, it is 1/4, so on and so forth. I'm gonna have to revert to that one for the sake of time. I'm really not remembering that one. Probably I could just provide it at another time or something. All right, so what we do is that we'd say 1t over half would reduce to a half. 2t over half, it will reduce to a quarter. 3t and a half. I come. Yeah, I know, Emily. Yes. Yeah, I know, Esther. All right, so yeah, I know, Emily. Yes. Yeah, I know, Emily. Esther. Oh boy. All right. And for forgive me. Here. Here you go. Yes. What about me? I'm coming, Esther. So t a half is equal to 116. Okay. All right, no more crying. So what we have here is that we have gone through 4 half-lives, and then the time period for the question is 4 days. That's what was said there. Yes, in 4 days it was reduced to that. So if it's a case that in 4 days we run through, yes, really. If it's a case that we run through 4 half-lives in 4 days, so it's 4 days total over 4 half-lives, then it would be 1 day per half-life. All right, so the half-life is 1 day. All right, that's how the long way of working that out. There is a shorter way, Just to remember the equation right now, but that's one way of dealing with it. So you show that 1 half-life reduces to a half, 2 half-lives to a quarter, 3 half-lives to an eighth, 4 half-lives to a 1/16th. And since it says that it is reduced to 1/16th over 4 days, then it's 4 days over 4 half-lives, which gives 1 day per half-life. All right, so that's one way in which you could solve a question similar to that. Yes, so that pretty much, as I said, the answers given here would have been for the May-June 2019 physics paper. So anything that is related to this paper, this is being covered, so you can just re-access it on the YouTube link provided, and you can go back to it and correspond answers to questions. All right, but pretty much that would be it. Now at this point, is there anyone that has any questions related to the paper or any other burning issue that you'd want to address? Yeah, I know, Emily. Right? Anybody? No? All right. Well, I'm pretty much finished with the paper, and I hope that whatever what has been discussed was beneficial to you and helpful. And I also wish you the best of luck in your exams to come. All right?
Thank you, sir. It was beneficial.
All right. I'm glad to hear that. So you all take care. All right?
Okay, sir.
Cool.